purpose of this training film is to give a better understanding of the stud welding process and equipment to operators, the inspection people, and setup people so that they can achieve better stud welding results on a more consistent basis. The principles of stud welding are adapted from arc welding. In manual arc welding, a flux-coated rod is used, a steel core, and it's held in an electrode holder. The sequence operations is the operator will touch the base material to initiate an arc, lift away from the base material, and then proceed with a travel and a desired length of arcing, and then at the end he breaks the arc by lifting away from the base material. In stud welding, rather than a coated rod, we have a stud with a flux in the center of it that's used with a ceramic ferrule that has serrations in it. The venting allows an escape of gases and contaminants. The stud welding process proceeds the same as arc welding in that the end of the stud starts from the base material, is lifted away from the work for a prescribed arc length distance by the solenoid in the gun. It's held for a prescribed length of time, amperage flows. At the end of the weld cycle, the stud's released and plunges into the molten pool of metal contained by the ceramic ferrule. The weld that results, the fillet development is uniform. The length of the stud has been shortened, the burn-off length during the weld process. The cross-section, the stud, we're treating the stud as an electrode. The whole end of the stud is burned off, and you get cross-section of a sound, dense weld. The equipment to do this, instead of the electrode holder, the front end of the gun has a chuck that holds the stud. Current passes from the cable in the gun through the chuck to the stud, the base material. The ceramic ferrule is held in a ferrule grip mounted on a foot. This foot held by the legs to the gun body. The ceramic ferrule goes around the base of the stud. The gun is positioned against base material. Plunge travel or extension of the stud through the ferrule is taken up. Then the gun is triggered, trigger button, the lift and plunge take place, and the weld is completed. The next topic I'd like to deal with is inspection of the welds after they're in place on the base material, and taking specifically a look at features of the weld fillet that will identify problems between good welds and welds that were too hot, in this case too cold, and ones that didn't have enough plunge or had a mechanical problem in the gun itself. Now, if we examine the weld fillets very closely, we can get clues from the fillet development that will indicate a change that would be needed in the setup of the time, the amperage, lift, plunge, or the tranquil arc and dampening in the gun. Other cases, we may possibly have ground or fixture problems that can be identified by looking at a weld fillet. A good stud weld onto clean base material is typified by a bright, shiny weld fillet with even height from one side to the other all the way around. The best indicator, though, is a bright junction of the fillet material into the base material. If that junction is a blend, a shiny radius, rather than material that is rolled under in a donut setting on top of the base material, you're then assured that you have bonded metal to the extreme edges of the weld fillet. If the metal is rolled under, you don't know how far under the material is rolled and where bonding begins and ends. The same weld setup as this onto material that hasn't had the mill scale removed is going to have more slag coming from the vents of the ferrule. This slag material is a product of the mill scale. We had the same burn off, the same wetting, bonding, but the mill scale acts somewhat as an insulator that keeps the fillet from giving you the bright radius of blend into the base material and adds to the amount of slag coming out the vents of the ferrule. Also traps pieces of the ferrule in the material between the vents. An extremely cold weld is typified by a dull rather than a shiny fillet. You have a dull gray porous fillet. The other indicator is that the material, the fillet material, comes out the vents, but it adheres to the vents. You end up with stringers or spider legs coming from the vents. The material was just barely molten and slag-like, sluggish, rather than a weld berry coming out and being expelled away from the fillet. It is just barely fluid enough to be squeezed out the vents, and rather than rolling away and separating easily from the weld, it adheres and traps the ferrule material between the spider legs. These welds, you may have not had enough amperage. The time could be low. The lift could be short. The same amperage over a short arc length gives you less heat than the proper arc length. The next weld is extremely hot. The weld berries are an indicator of too much heat. You get undercutting in here. The back side of this one is severely undercut. You have a gouging into the base material, washing away of the material. The amperage setting or possibly the time were way too high on this one. The other one that gives the appearance of being too hot, you have the undercutting. This was done at a normal amperage, but it had a restriction in the gun motion, either through not having adequate plunge set or a gun that needed maintenance, or possibly the Tranquil Arc plunge dampener was set for too slow a dampening rate and the stud didn't get down into the base material. Checking the before weld and after weld length of the stud can give you a clue of whether there was a hang-up or insufficient plunge. The extreme case of a hang-up will just be a stud that comes off in the gun. An operator could get this same effect by lifting the gun off from a welded stud too quickly. Again, the good weld is bright and shiny, even fillet development, and a blend into the base material at the edges of the fillet.